All right, so our objective today is to learn about isosceles triangles and the theorems associated with the isosceles triangle. To learn about isosceles triangles that's going to be one of them. And then also understand theorems about isosceles triangles. Okay, so this is going to come out of lesson 4-4, so you can read through that in the book. And we're going to start with, let's talk about isosceles triangles. So let me draw one. And what do you guys know about an isosceles triangle? I think we talked about it in an earlier chapter. So what do we know? Isabel.
At least two sides.
Or Isabella, sorry.
At least two sides are congruent.
Oh, thank you for remembering that piece, that at least two sides are going to be congruent. We could have all three of them and be called it. Okay, so let's pick these guys as the two sides that are going to be congruent. Okay? Now, we're going to talk about all these different parts and label them. And you're going to make vocab cards of these. So first off, let's talk about the angle that is formed by those two congruent legs. Okay? He has a special name. He is called the vertex angle. And the vertex angle is the angle formed, I should say of an isosceles triangle. That's part of its name. It's an angle formed by the two congruent sides of an isosceles triangle. And I'm going to abbreviate isosceles triangle as isos. It's also opposite the base of the triangle. Okay, so let me add a couple things here. He's the base. He's opposite the vertex angle. He's not one of the two congruent sides. And what do we call the other two sides? Does anyone know that? Same term that we use when we're talking about right triangles.
The legs.
Okay, they would be called the legs. Okay. All right, let's talk about the two angles that are formed at the base. You'll never guess their name. They're called base angles. And then of an isosceles triangle. And they are angles formed at the base of an isosceles triangle. Or you could say that the base is a common side of these two angles. Okay, that would be another way to think about it. Okay, and then I did write up here, so let's give him a definition. Legs of an isosceles triangle. And that's just going to be the congruent sides. Of the isosceles triangle. Okay? Now here's the good news. The first theorem I have to share with you has a name. So when we use it in a proof, we just need to list the name out. Okay? All right. First theorem. of the day. This is theorem 4-1 because it's the first theorem in the chapter. We've only had postulates up to this point. That's kind of interesting. Here we were fourth lesson and first theorem. This is called the Isosceles triangle theorem. And it says, if two sides of a triangle, notice it doesn't say of an isosceles triangle, it just says of a triangle. If two sides of a triangle are congruent, which by definition we would be able to say, oh, it must be isosceles, then the angles opposite those legs are congruent. So let's go back to that diagram we drew. What angles are they talking about that would be considered opposite the congruent legs? The base angles, okay? So there is kind of another way people describe this, and I'm going to do a different color because the actual theorem for our book does say two sides of a triangle are congruent, then the angles opposite those legs are congruent. The interpretation is that base angles of an isosceles triangle are congruent. Now, the reason why you cannot write this down on your card is because the theorem itself doesn't mention that you need to have an isosceles triangle. What I wrote down in green specifically states you have to have an isosceles triangle. So in your given, you don't need to be told you have an isosceles triangle. You could be given that you have a triangle that have two sides that are congruent. But the theorem doesn't say I have to prove first that it's an isosceles triangle. I just need a triangle with two congruent sides, and then I can assume that the two angles opposite those sides, which we know are base angles, would be congruent. Okay? So let's go ahead and do a proof of this. I'm going to go to, I think, the next screen so we have more room for this. So our proof is, here's our diagram. And this is how all that we're told. Segment AB is congruent to segment AC. And our job is to prove that angle B, oh, that doesn't look like a B at all, sorry. Angle B is congruent to angle C. Now, here's the problem. I have nothing that's going to help me prove that. But what have we been studying in the last lessons?
Auxiliary line.
Okay, and what's the auxiliary line going to do for us in this one, Dakota?
Help us prove things.
Like what? Things is not a very
Like triangles are congruent.
good. So if I draw an auxiliary line appropriately, then that's going to allow me to create two triangles. Then if I can prove the triangles are congruent, I could use CPCTC to get angle B and angle C congruent. So where do you think I should be drawing that auxiliary line?
Right in the middle.
Okay. What middle? I got lots of middles.
Right to the middle of point B.
So using terms we just talked about from the, what kind of angle? Vertex angle. Down. Okay, so here's my question. If I just did it like this, would that work?
Yes.
Okay. All right. I need to come up with three things, right, that I can prove are congruent in order to do this. So that's not going to work. So, Mikey, what do you think?
I need to do the angle bisector.
Okay. So if I draw this specifically in such a way that I bisect that vertex angle, do I have enough information to prove those two triangles are congruent?
Yeah.
I do now because I've got a side that they have a congruent from the given. I have angles that are congruent based on how I drew that auxiliary line. And I have a reflexive side, right? Okay, now, I do need to add a letter, right? Okay. So here's the deal. I need to give a reason for that auxiliary line, but I have to be very clear about how I draw that, because I want to do it in such a way that it bisects that angle. Because if I don't do specifically that it bisects the angle, I'll only have two pieces of congruence, and I don't have a third, and I can't prove the two triangles are congruent. Okay? So let's start with the given. That segment AB is congruent to segment AC. Oops. Forgot that over there. So when I talk about my auxiliary line, I'm not just going to say draw segment AB. I'm going to say draw segment AB in such a way that I know that it bisects the angle BAC. So draw, I always start all my statements for auxiliary lines with the word draw. Draw segment AD so that it bisects angle BAC. Now, do we have a theorem that talks about bisecting an angle? Drawing a line so that it bisects an angle. Okay, Mikey?
Angle bisector theorem.
And that angle bisector theorem says that angle BAD would be half of angle BAC, and that I haven't written anything. So here's the deal. What do I know is true about angles that are bisected? I would get two congruent angles, right? So what do I know that allows me to measure angles to prove that they're congruent? Drake? Okay, no definitions. Okay, yeah, because you guys are reading in your book. Very good. The protractor postulate actually allows me to draw that line so that angle BAD and angle CAD will be exactly the same size. So that's what I'm going to use. Now this doesn't happen very often using protractor postulate. This is one of the rare times it shows up. So here's how you write this. Through the protractor postulate, there is exactly one ray that can bisect an angle. So we've asked this ray, AD, to bisect angle BAC, and there's only one ray that can meet that job. Okay? So that's how I use protractor postulate in this particular case. All right. So now that I have an angle bisector, the definition of an angle bisector says I get two angles that are created. Now, I got to look at the orientation. Are my two triangles facing the same direction? No, they're kind of facing opposite directions from each other. So angle BAD, now remember here in the proving, B and C correspond, so this would be angle CAD. That's your definition of an angle bisector. Not of a bisector, an angle bisector. And then we have our third piece is that segment AD itself. It shows up in both of the triangles. So that's your reflexive property. Of congruence. So I have three corresponding pieces that are congruent. So I'm able to get to my conclusion. So triangle, and I'm just going to use the letter orientation from the angle. Triangle BAD would be congruent to triangle CAD. And what's the reason? SAS. SAS postulate. Now that I've proved the two triangles are congruent, all six corresponding pieces, that would be three angles and three sides, are going to be congruent. So I just need to get the two that they asked me to, that angle B is congruent to angle C, and the reason would be because corresponding parts of congruent triangles are congruent, so CP, CTC. Okay? Since this theorem, and this is proving the isosceles triangle theorem, that's what this was, a proof of it, That's why I couldn't use isosceles triangle theorem in this proof, because I was proving it. Since it's such a big deal, there's a lot of stuff we can gather from it, so we are going to have some corollaries like we did last time. So first is corollary 1 to theorem 4-1. And that corollary states an equilateral triangle, so all sides are congruent, is also equiangular. Equilateral triangle, all the angles are the same. They all measure 60. The other thing to keep in mind is if you have an equilateral triangle and it tells you that it's also equiangular, the relationship that exists between the sides mirrors the relationship between the angles. In other words, if I have an isosceles triangle where I have exactly 2 congruent sides, then I'm going to have exactly 2 angles that are congruent. Okay? If I have all my sides are different lengths, all my angles are different lengths. So there is a direct relationship between what the sides look like and what your angles look like. Okay? Corollary 2. To theorem 4-1 states an equilateral triangle has 3 60-degree angles. And so we combine that back with, I think it's theorem 311, where we take the number of sides, we subtract 1 from it, or 2 from it, and then multiply that by 180. So the sum of the measures of a triangle is 180. And then I think we even have a corollary that states that. So if I have all 3 angles that add up to 180 are the same, divide 180 by 3 and you get 60. So we can prove it with our other information. And then we have a corollary 3 to theorem 4-1. And remember, these corollaries and theorems just help us get to an answer faster. It says the bisector of the vertex angle of an isosceles triangle is, oh, this is interesting, perpendicular to the base at its midpoint. Okay, whoa, that is a lot to take in. So let me draw a picture of this so we can kind of analyze it. So we've got an isosceles triangle. And this is saying that the bisector of the vertex angle is 2 things. 1, perpendicular to the base. 2, at its midpoint. Come on, help me out here. So we get, let me put some letters in here. So according to this theorem, these are all the pieces of information I can get from this. We have segment BM bisects angle ABC. It also says that segment BM is perpendicular to segment AC. It also says M is the midpoint of segment AC. Wow. That's going to be really helpful in a proof. That's a lot of stuff I can get from that one. Alyssa.
Did you write all of that in one step and then just put that, or would you have to do each one separately?
You would have to write them out separately, okay? And I'm going to be honest with you, you would not be using all three of them at one time. You'd only use a piece of that for whatever you needed. Like, let's say you needed these two angles, BMC and BMA, to be congruent to each other. Then you could state from this corollary that segment BM is perpendicular to segment AC, and then you would say those two angles are congruent because if perpendicular lines form congruent adjacent angles. So that would be the only piece I'd be interested in. If I wanted to... The given is that we have a bisector, so we already know that. But then I could say that M is a midpoint if I wanted to prove that segment AM and segment CM were congruent to each other. So it depends upon what I'm trying to gather. I'm only going to pull out the one piece that's important to me. Okay? So guess what? More theorems. What are you talking about? Theorems are awesome. Oh, blah, blah, blah. Theorem 4-2. If two angles of a triangle are congruent, then the sides opposite those angles are congruent. So what does that sound like? I just heard, say it again, kind of.
It's the converse of theorem 4.1.
It is. It's the converse of the, and because it has a name, isosceles triangle theorem. Notice again, it doesn't say that you have an isosceles triangle, it just says you have a triangle, but it meets a special condition. So basically, it'll come back. It's telling you that the two angles that are congruent would be considered the base angles. And so now you just have to find those congruent sides. Okay? Now, I also have a corollary to this one. And because there's only one corollary, I don't write a number next to it. And it states an equiangular triangle is also equilateral. And if you think about it, lateral. That's the converse of corollary 1 to theorem 4-1. So that makes sense that we would have converses in both of those. All right, so I've got one more proof. One more proof. Isabel.
Can you use the corollary to the theorem when you're proving that theorem?
No, because it comes after. So you can't use a corollary to a theorem if you're trying to prove the theorem because it comes after. So the order that I give you is the order you can use it. Okay? So could I use theorem 4-2 to help me prove corollary 4-2? Yeah, I could because it came first. Would I? I don't know. Okay? But again, I can only use what came ahead to help prove something that comes after. Okay? John.
Could you use theorem 4-2 to prove that a triangle is an isosceles triangle?
Yes. If your ultimate is prove that you have an isosceles triangle, if you could prove that you had two congruent sides in this triangle, then you could do that. Yeah. Okay? All right, so let's do our last thing. Here's our diagram again. And we're given this time that angle B is congruent to angle C, and our job is to prove that segment AB is congruent to segment AC. So think about it. We were proving the isosceles triangle theorem in our last proof, and the proof in this theorem was the given. Yeah, so it's the converse of the information. So this is what I know. And again, we have the same exact problem. That doesn't help me with anything at this point. So in order for this to work, we're going to have to, again, create two triangles. And to do that, we're going to drop that auxiliary line. But again, we're going to drop it in a very specific way. We're going to drop it so that it bisects that angle again. Okay, so we're going to drop it so that this becomes true. And we'll call that point D again. Okay, so now I've got two triangles, and here's where it gets a little bit interesting. I've got the reflexive, but it doesn't give me SSS, SAS, or ASA. Because for it to be ASA, I would have to have segment AB congruent to segment AC, which is what I'm trying to prove. So what else could I do? Rachel?
Well, the auxiliary line bisects, or it is perpendicular to line to segment BC.
We don't know that. Okay. What you got, McKenna? Or Michaela, sorry.
The corollary 3 and Pamfordas line a bisector of the vertex of an angle of an isosceles triangle is perpendicular to the base of the midpoint.
Here's a problem. We don't know what's isosceles. We're trying to prove it is, basically, by saying those two sides are congruent. So all of those are gone. I guarantee you we have a theorem that we can use. While you're looking, I'm going to write.
No, don't do it. Don't do it.
Because the side that they have in congruent is not included between the two angles. Actually, what we have is a naughty or actually we have angle side, which we don't know anything about yet. Okay. So, again, we're going to draw that auxiliary line in such a way that we can get two congruent angles. And how we're going to do that is by bisecting that angle. So we're going to do exactly the same auxiliary line definition that we did before. So you're going to draw segment AD so that it bisects angle BAC, and we're going to use the same reason through the Protractor Postulate. There is exactly one ray that bisects an angle. Notice that the reasons are written in a general way and not a specific, that there's exactly one ray AD that bisects angle BAC. We don't write that in our reason. We write that in our statement. Okay, yes, you would. Don't do it. Okay, so from there we can at least get segment AD is congruent to itself through the reflexive property. Okay, so the two angles we have aren't working for us. We need the third angle, because then that would give me the angle BAD, segment AD, angle BDA. It would give me angle CAD, segment AD, and angle CDA. So what can I use? What you guys find? Sarah?
I forget which one it is, but it's like if two sets of angles, like there's two triangles and there's two sets of angles that are congruent, then the third set is congruent.
Exactly. We have a theorem. It's actually corollary 1 to theorem 311. If two angles of one triangle are congruent to two angles of another triangle, then the third angles are congruent. So the reason why we had to draw this bisector was so that we could actually get the third set of angles to be congruent to each other. Okay? So we're going to get angle ADB is going to be congruent to angle ADC if two angles of one triangle are congruent to two angles of another triangle, then the third angles are congruent. So now I've just added this. So now I've got red angle, segment AD, green angle. What is that? ASA. So my two triangles, and oops, sorry. And I'm going to just use the lettering from here. So triangle ADB is congruent to triangle ADC, and that would be ASA. And then I can get the corresponding side, segment AB, is congruent to segment AC through CPCDC. Okay, there we go.